Okay, so I'm going to give you a guided tour here of section 13.2, and then we'll look at a few examples. But line integrals. Now, it comments here that in this section we define an integral that is similar to a single integral, except that instead of integrating over an interval from a to b, we integrate over a curve c. Such integrals are called line integrals, and they were invented in the early 19th century to solve problems involving fluid flow, forces, electricity, and magnetism. Okay, so let's see here what we have. So in figure one, they show a curve C in the XY plane, and the curve, every point on the curve corresponds to a different time value. So at the initial point P sub 0, time is equal to A, and then the last point P sub n, time is equal to B. Okay, and when you move along that curve, okay, it could be like, for instance, a particle moving along that curve. The particle moves along that curve corresponding to some parametric equations that are functions of t. So, for instance, okay, the parametric equations, you can represent them. Hold on here. Did I lose the, hold on. Somehow I lost the ebook. Let me get it back. Okay. So there are parametric equations for a particle moving in two-dimensional space. And if we wanted a particle to move in three-dimensional space, we would just have three parametric equations. Okay. So everything I'm going to talk about here is applicable to line integrals in three-dimensional space. So, okay, now what do we want to do? What do we want to do? Well, what we want to do is we want to, and maybe I can have both of these show here in the diagram. One moment. Okay. So you see there in figure one that curve C, and you have these different points on the curve. Every point has an XY coordinate. Now, let's say there's a function of two variables whose domain includes the curve C. In other words, the function acts on all the coordinates in the XY plane, and those coordinates also include the points on the curve C. If we take that function value at xi, yi, and multiply by delta s, which is a piece of arc length, okay, so like for instance, from the point P sub I minus 1 to the point P sub I, well, or let's say from the point P sub, yeah, from the point P sub I minus 1 to the point P sub I, you're moving a little piece of arc length, right? So the point x sub I, y sub I is on that arc, and you know, if you go the length of that little arc there from point P sub I minus 1 to point P sub I, you've moved a little arc length. What if we were to take the function of at the point x sub I, y sub I, and multiply it by that piece of arc length? And what if we were to do that for every point on this curve, on this arc? Okay. Well, what you would be finding is something that will resemble the area of a curtain. Okay. So what you see here, what I'm trying to say is, What I'm trying to say is this sum here would resemble the area of a curtain, okay, along that curve C or arc C, because the function value is a height and delta S is an arc length. And length, so it's like taking length times height, that gets you area. So they have a little picture that shows that in figure 2. This is really geometrically what the arc length stands for. It's the area, it's that area where you have points on a curve C in the XY plane. You're evaluating each of those points on that curve C. You're taking the function value of each of those points on that curve C, and that gives you the heights, those little heights there. And you take the height of each little rectangle there, and the height's determined by the value of the function. You can see it right there. They show the f of xy right there. And you multiply each of the heights by the piece of arc length, and that gets you the area of the curtain. And this is what's called a line integral of your function f along your curve C. That's what we call that. Okay, so this is how formally the line integral is defined. It's a line integral of a function along curve C. Are there any questions from this in section 13.2? Are there any questions at all? Who's feeling good so far? Maybe give me a thumbs up if you're feeling good. Thank you, Gordon. Thank you, Malik. Thank you, Ellie. Thank you, Emma. Thank you, Madeline. Wonderful. Okay, good. And a few other people too. What happens is it shows me like who gives a thumbs up, but after like 5 thumbs up, it stops giving me that, and then I have to, and then so that maybe the last few of you, thank you. I might have missed giving you credit for that. Okay, so what, if you look at that integral, what kind of makes that integral difficult? Okay, what makes that integral there, that line integral? You're integrating across some curve C, f of xy ds. What makes that integral a little difficult to sort of maybe compute? What would make that difficult? Can anybody offer a thought? Good, excellent, Ellie. That's exactly the word, what I'm looking for. That line integral, you're integrating with respect to s, arc length. We are used to integrating with respect to x or y, you know, or z, for instance. So it would be good if we could find an equivalent formula where we integrate, or with respect to t, right? We've integrated with respect to t also. And in fact, what we want to do is we want to change, we want to rewrite this line integral in an easier form. Well, okay, you found lengths of arcs before, right? How many remember doing this in calculus 2, finding the arc length, and this is your arc length formula? How many remember that? Sure. So Juliana remembers that, and so we can essentially, you know, delta S could, when that original Riemann sum that we looked at, if I go back up here, the original Riemann sum delta S, well, delta S could be represented by, I mean, it's a piece of arc length. So why not just then incorporate the line in the arc length formula into our formula. And so this integral, which is this line integral, which is difficult to work with because it's with respect to, we integrate with respect to arc length, we can rewrite the line integral this way. Where, and x and y, those coordinates on the curve C are functions of t, and ds can be expressed as the square root of x prime squared plus y prime squared dt. So one way to think about this is like this. Let me go to the whiteboard. Let me go to the whiteboard here, because I want you to feel comfortable with the formula. So arc length, which we normally denote by L, can be thought of as the integral from A to B. Well, it is this, right? Of dx dt squared plus dy dt squared dt, right? And let me just see one thing here, class. One moment. One moment. Checking one thing. One moment. Okay, so there's something I'm wanting to do here. Just give me a moment here. This is not, well, hold on here. This is not exactly the way I want to do this. Let me do it differently. Just give me one moment here. I'm going to come back to this formula. Okay, I'm going to come back to it. But let me just, this is the arc length. This is the formula for the integral with the line integral with respect to a curve C. Okay. But let me just, I want to check one thing here before we move forward. Okay, this is what I wanted to show you here. Where's my pen? Okay. So if I draw a right triangle here, and let's say I have Okay. Let's say I have some arc, and for a very short distance, hold on here. I'm going to call this delta S. So what I'm trying to say is the line segment from here to here is approximately the little piece of arc length, the little red piece of arc length. So I'll call that delta S. I'll call the horizontal distance here in my right triangle delta X, and I'll call the vertical distance delta Y. So delta S squared is equal to delta X squared plus delta Y squared, right? So that means delta S is equal to the square root. That's by the Pythagorean theorem above. So delta S squared, or delta S, equals the square root of delta X squared plus delta Y squared, right? Okay, so let's see here. I mean, this is absolutely true, absolutely true. And we could say that delta S over delta T is equal, let's see here, it equals delta X squared plus delta Y squared all over delta T. Okay, but delta T can be written as delta T squared square root. So this means then that delta S divided by delta T is equal to the square root of delta X over delta T squared plus delta Y over delta T squared, right? So far, so good? Please let me know if you're uncomfortable. All right, Yunu's good. All right, so good. Thank you, Ellie. Thank you, Juliana. All right, so this means then that, let's say this the right way. Delta S would be equal to the square root of delta X over delta T squared plus delta Y over delta T quantity squared times delta T. Okay, so let's make sure. Let me just fix my fix this arrow a little bit here. Clean this up a little bit here. Okay, so what I'm doing here is I'm going from like step 1, step 2, to step 3 to step 4. And now I'm at step 5. And this would mean then that ds is approximately what? This is our final step, step 6. ds is approximately equal to something squared plus something squared, and then something. What would it be? So when you let time get small, delta S over delta T becomes what? What does delta S over delta T become? In other words, delta S divided by delta T. Okay, let me phrase it another way here. Let me phrase it another way. Let me just phrase it the way I want to phrase it. Delta S over delta T would be approximately what for delta T small? Delta S over delta T, the change in S over the change in time would be approximately equal to what when delta T is very, very, very small? Think of calculus. What do I want here in the numerator? What do I want in the denominator? That's right, Ellie. Exactly right. Right? So, I mean, what is delta S over delta T? That's the slope of a secant line. But how many remember the secant lines as you let the denominator, usually call it h, as h goes to 0, the slope of the secant lines approach the slope of the tangent line. How many remember that in calculus 1? I mean, it's been a while, but that's true, right? Yeah, so all I'm saying is that the ratio of these two of delta S and delta T, okay, hold on here, one moment. Hold on. What I'm doing is I'm looking for the right terms here. One moment. So the ds and dt are differentials, right? But basically the idea is just that the slope of the secant lines as delta t gets small, or you could as that gets small, that's gonna approach the delta s over delta t will approach the derivative of s with respect to t. So now what I'm saying is when t is small, when delta t is small here, okay, so I'm focused on 6 here now. Focused on 6. ds is approximately equal to something squared plus something squared something. Well, what's going to go here, class? What's going to go here, you think? We had a delta t here. We're going to have a dt here. Good. Good, Hunu. and we had a delta x, delta t here, what's going to go here? What's going to go right here? That's right, dx dt. And what's going to go where delta y, delta t is? What's going to go there? That's right, dy dt. So ds is approximately equal to the square root of dx dt squared plus dy dt squared dt. And so now, when you go into the blackboard and you see this conversion from an integral with respect to arc length to an integral with respect to time, and ds, they're replacing with the square root of dx dt squared plus dy d squared dt, are you more comfortable with that formula now? Are you more comfortable with that? Okay, who's a little more comfortable with that formula? Good, Ian. Good, Ellie. Good, Juliana. Thank you. All right, so good, Charles. You know, I want this to be fun, you know. Thank you, Kino. I want this to be fun. Well, math will be fun if you understand what's going on, right? And so, hey, okay, all right, this is cool. This formula is cool. I know why the formula. We know why the formula is true, and now you know we can apply the formula. So, like for instance, if we go forth here and look at an example here, they want you to compute in example 1 a line integral along a semicircle. Okay. Well, okay. How do we get the semicircle? So the curve C is the upper half of the unit circle x squared plus y squared equals 1. And this means then that, okay, well, the parametric equations that will trace out that circle are x equals cosine of t, y equals sine of t. And incidentally, what should t go between? What should t go between if I want the upper half of that circle? Starting value of t would be 0. What would the ending value of t be? Pi. Very good. Very good. And so, okay, well, we have the parameterization of our curve. And okay, now it's just a matter of applying the formula and computing out the line integral. That's what you're doing. Okay, are there any questions on that? And obviously they left out some work. You'd have to make a substitution on that third integral where you have cosine squared t and sine t. You're going to let u equal cosine t, right? But they leave out steps. They leave out steps. But of course, when you show your work, you put in the steps, right? They're just trying to save a little money. That's all. Less paper. Any questions on this problem before we move on? Okay, very good, very good. Let's move on then. Let's move on. So sometimes you have a curve where it's not where the curve, like in figure 4, you have a curve that's piecewise smooth. In other words, the curves themselves are all smooth curves, but it isn't just one curve. It's like in that figure 4, you have 5 curves, smooth curves connected together. Well, okay, what if you have a particle that moves along that path? Could you find the line integral for that? Yes, you could. It's just how many, like in figure 4, how many line integrals would you need to compute and add together to do something like in figure 4? That's right, Ian. You'd have to do 5. Okay. Now in the book, what they do is they do an example where they want you. This is example 2. They want you to evaluate this line integral with respect to the curve C. where C consists of an arc of a parabola followed by a vertical line segment. Okay, and in this problem, if we go to the picture here, this is our curve C. So there are two separate, there's the parabola curve C1, and then there's the line segment C2. And we have to get the parameterization for each of those curves. Okay, so when we do that, let's start with the parabola. Now, usually what I like to do is I like my parameter to be t. But you don't have to let your parameter be t. You could, like the parabola, if you were to let your parameter be x, okay, if you were to let your parameter be x, okay, hold on, I don't want it to, it's one moment here. Yeah, just this, please. Yeah, if you were to let your parameter be x, then x would go from 0 to 1, and y would equal x squared. Okay, and now what they're doing is they're computing the line integral below, but the parameter is x. Okay, so you see how the square root, under the square root, they don't have dx dt squared and dy dt squared. They have dx dx squared and dy dx squared because they're treating x as the parameter. I mean, it's okay to do that. It's okay. And they end up getting 5 root 5 minus 1 over 6. If it were me, I probably would just let x equals t and y equals t squared for that parabola, and then t goes from 0 to 1. That's how I would do it. But, that's what they do. Okay, are there any questions? All right, well, let's keep rolling then. Hold on. One moment here. I want to get this off. Now we have the, hold on here. Now we have that curve C2, which is just a vertical line segment going from 1, 1 to 1, 2. Okay. So for there, you have to come up with the parameterization. And what they do is they say, okay, well, let's let x equal 1 because, well, it's a vertical line. So the x coordinate is going to be 1 for all the points, and y will equal y, and y goes from 1 to 2. And so when we do that, there's the parameterization, and now they go forth, and they compute the line integral for that second curve C2, and they get 2. So you notice here for this second curve, the y is the parameter. Y is the parameter. Okay. And so you have not dx dt, but dx dy squared, and you don't have dy dt, you have dy dy squared, and that gets you, that'll work out to be a 2. Are there any questions on this? Please let me know. How many of you, incidentally, would just like to use the parameter t for your parameterization as opposed to like an x or a y? How many would prefer to be kind of consistent and just use like t all the time as your parameter? Okay, I'm with Charles and Ian on that. That's just my personal preference, but people are different. Kino agrees. Okay, and but everybody's a little different. Okay. So then the full line integral. The full line integral, we would just add the two line integrals up. And WebAssign wants exact answers, so that would be the answer you do. And there are a lot of cool applications dealing with line integrals. You can, for instance, And we're, you know, you can, for instance, let me just go down here a little bit. And this is something now, you know, my area, my PhD is in mathematical statistics. I've had a lot of math. But like this here, the center of a mass of wire with density function rho is not something that I've done in my math life. But how many have heard of the center of mass of a wire with the density? Okay, located at that centroid. How many maybe have seen formulas like this? Okay, good, good. And so, you know, hey, oh wow, there's the line integral. There are those line integrals right there for the center of mass. So, you know, it comes up in physics courses. Excellent, excellent. Okay, now our integral is with respect to t. Okay, our integral is with respect to t. Okay, and if we let's say, you know, like well, let me go down here and show you a few more line integrals. So here we can have a line integral. Well, the line integral we did was with respect to arc length. When you have the integral with ds, it's with respect to arc length. But we're able to compute that now. But you can also have line integrals with respect to x, for instance. Okay, so, and with respect to y. Okay, you can have those line integrals as well. Okay. Okay, so the formulas for those, let me just go down here. If you're doing a line integral with respect to x or y, those are the corresponding formulas. So notice the square root is gone, right? The square root's gone. Now, why would that be? Why would that be? Let me show you why. Let's do the line integral with respect to x, the top formula. Let me go to the whiteboard. So recall that we showed that delta s was equal to the square root of delta x over delta t squared plus delta y over delta t squared. Hold on, I got one too many parentheses here. Okay, and then, you know, we have our delta t here. Now, you can have, you know, we talked about like a curve, an arc that was curved, but you could have a flat arc. You could have a flat arc like that. Okay, and in that case, delta s would equal what? For a flat arc, a horizontal arc, the arc length would equal what? Delta s would equal delta what? When the arc is flat and horizontal, this distance here is the distance of what values? X values or Y values? This distance. X values. Sure. I mean, we know that, right? We know that. I mean, you know, here's, hold on here. You know, here's 2 Here's 5. Hey, what's the distance, everybody? 3, right? You took a difference of x values. So in the case of a horizontal arc, delta S will equal delta what? What's going to go here? I'm looking for a variable. What has to go here when you have a horizontal arc? Delta S equals delta. What's the right choice going to be? X. Good. X. Delta S equals delta X. I mean, this is so like when you see an arc, right? When you see an arc and you have 2 points and you want to know the distance between the 2 points, that's some piece of arc length, right? But if the arc is in a perfectly horizontal arc, delta S would just be equivalent to delta X, right? And so what happens is then in this case, delta S in the formula above, well, that would be delta X over delta T quantity squared plus what over delta T squared. What's going to go? So what I'm doing is I'm pointing out this special case here where delta S equals delta X. So you have delta X over delta T quantity squared. And then what's going to go here? What's delta Y equal to? 0. That's right, Ellie. There is no delta Y. It's a perfectly horizontal arc. Okay, so that's then what you're going to get. Look at what happens. This goes out, and you're left with the square root of delta X over delta T squared. That's going to get you delta X over delta T times delta T, right? And what happens to the delta T's? They simplify out, leaving you with delta X. Okay, so in other words, in the arc length formula, what I'm trying to justify is I want to say it the right way, is the following. If we go back to not the arc length formula, the original line integral formula that we worked with, okay, hold on, where's the formula? Here it is. Wait, let me share it. What I'm trying to say in this original formula that we have, which should always work no matter what the arc looks like, if we have a horizontal arc, then ds would become what? ds would become d well, hold on. Let me go back here. Hold on. Let me go back. Let me do this again. This is important. Let me just do it again here. Let me rephrase it. I mean, it's so important that I wanna do it right. Okay, let's refresh ourselves. So Okay. Okay, so here, for a horizontal arc, delta S equals delta X. Okay. Delta S equals delta X. So let's see here. And delta Y equals 0. Okay, so the arc length formula would we got a square root here. dt here. Okay, so again, we have delta x over delta t squared plus delta y over delta t squared. Now, being that delta y equals 0, okay, what would dy dt equal? What's dy dt going to have to equal? 0. Excellent. So this is going to give us the integral from a to b of f of x t, y of t, okay, times the square root of all this here dt. But basically, we just have the square root of dx dt squared. So all that's going to give us, and I mean, what is this? This is the same as x prime of t squared, right? Right? That's what that, hold on, let me get a little, like my stuff to look good. Okay. So the x dt squared is like x prime of t squared, but we're taking the square root of it. So then that's going to give us x prime of t dt. And that's one of those formulas that you saw in the formula box 7 from section 13.2. This is the integral, or the line integral, with respect to x. Okay. And if we go back to the book here, okay, so this was the line integral with respect to the arc length when we're doing, with respect to ds, and then that full formula there is the line integral with respect to arc length. But then the line integral with respect to x would be that top formula there in formula 7. Okay, and then obviously with respect to line integral with respect to y would be the second formula. Are we okay with those formulas? Are we all right with those? Okay, Malik's good, excellent. And Juliana's good, all right, wonderful, wonderful. Okay, so we're seeing some formulas that might seem a little strange, but they're not strange. We know why they're true. We know why they're true. So, okay, let's continue on here. So, one thing here that they mentioned that it frequently happens that line integrals with respect to x and y occur together. When this happens, it's customary to abbreviate the sum of the line integrals, one with respect to x and one with respect to y. It's customary to abbreviate it with a single line integral on the right there over the curve C, pxy dx plus qxy dy. So what P and Q are, well, P and Q are just functions of x and y. So that's a notation that is common. I'm thinking that movie with Russell Crowe, A Beautiful Mind, about the economist John Nash, this kind of notation rings a bell in that movie. I don't know if any of you've seen that movie. It's probably about 15 years old now. But he's like writing on the stained glass windows in the library, and like all these integral formulas, and this rings a bell. But at any rate, let's move on here. So, okay, so parameterization is very important in section 13.2. So if you need to parameterize a line segment, this formula will always work. Okay, this formula, if you have a line segment that goes from one point to another point, so long as you know the initial point, or r sub 0, and the end point, r sub 1, this formula will always work. And they utilize that formula. In the next example. So here they are saying in example 4, let's integrate along two curves with the same endpoint. So what they're going to do is, if you notice here in figure 7, okay, in figure 7, you have an initial point, -5, -3, and a terminal point, 0, 2. And what you want to do is you want to compute two line integrals. Well, I want to be careful. The sum of two line integrals. But along the line segment C1, you want to compute that. And then along the line segment C2. So how would you do that? Well, of course, along the line segment, and by the way, here is what they want you to find. Okay, but that notation means find the sum of two line integrals, one with respect to x and one with respect to y. The line integral with respect to x involves the function y squared. The line integral with respect to y involves the function x. Okay, and in part A, you have this line segment from -5, -3 to 0, 2. Okay, and so using the formula above, using this formula here, okay, where t goes from 0 to 1, they use that formula where r sub 0 is the point -5, -3, and r sub 1 is the point 0, 2. They use that formula, and this is the parameterization that they get. Hold on, let me get that blue off. Sometimes you can't, there. Well, sometimes the blue's just there. What can you do? It's okay. There's the parameterization. Okay, so sometimes for a line segment, it's kind of, I mean, and parameterization can take, there are many different parameterizations of a line segment. But that formula above, in the formula 8 box, gives a quick way to just, hey, here's the parameterization. So in this case then, dx dt, since x is 5t minus 5, then dx dt is 5, which means dx equals 5 dt. That's what they're noting here. I'd like to try to just highlight it. Hold on. Come on, get off there. Okay, so dx dt is equal to 5 because x equals 5t minus 5, so dx dt equals 5, and therefore dx is 5 dt. Y is equal to 5t minus 3, so dy dt equals 5, so dy equals 5 dt. Okay, and so the you have your dx and you have your dy, and I want to comment here. I want to comment. Let me just go to back to the whiteboard real quick here, because I'm trying to fill in some details for you so you're comfortable with this section. So let's see here. This, like, let's take the line integral with respect to x. That's equal to the integral from a to b of f of xt, comma, y, t, and then x prime of t dt. Now, we know that dx dt is equal to x prime of t, right? So therefore, dx will equal x prime of t dt. And so what they're doing is they're replacing x prime of t dt with dx. That's what you're seeing in example 4. Okay, are there any questions on that? Similarly, the integral with respect to the line integral with respect to y okay, well, you know it. As this line integral, right? Well, all right. Here, you know, dy dt is equal to y prime of t, so dy is equal to y prime of t dt. And so now they're replacing y prime of t with dy. Are there any questions on that? Maybe give me a few thumbs up if you're good with that. Okay, excellent, excellent. Well, then let's go back to the book here. Okay, so in this example, then, based on the fact that dx is 5 dt and dy equals 5 dt, hold on, I don't want that. Highlight it. Does what you see then in the yellow box, the computation where they're adding the two line integrals, does that make sense? For the curve C1, right? That was the well, yeah, that's the line segment. Are there any questions on that computation? Maybe give me a thumbs up if you're comfortable with it. Okay, good, good. Excellent, excellent. All right, you're coming a long way here into this section. Good. Excellent. Thank you, everyone. Well, okay. That being said, now for part B, they wanted you to now in Figure 7 find the sum of those line integrals over that parabola, x equals 4 minus y squared. So what they do is they say, okay, well, we can use this parameterization. If we let y be our parameter, then x is 4 minus y squared, and y goes from -3 to 2. Okay, and so then let's see here. Dx equals -2y dy, and dy equals dy. Okay, and so let me just see here. One moment, class. See, I like the T parameterization. It just makes it easier for me personally. But they work it out. And you get 40 and 5/6 as your hold on here. Let's see if I can highlight that. Yeah, you'll get 40 and 5/6 as the sum of the two line integrals across the path C2. So this is how, but again, personally, I don't like my life to be complicated. So I always like to use my parameterization with the T is my parameter, because then, I got my formulas, and it's just easier, for me. But everybody's different. Okay, and you do as you feel comfortable. All right, I want to keep going here. I'd like to finish up this section before we take our break. So moving on here. So we talked about line integrals in a two-dimensional xy plane, but we can also have line integrals in three-dimensional space. And all the formulas you learned are analogous for three-dimensional space. It's just you have a third variable. So the line integral, if your particle is moving along some curve in three-dimensional space, then the line integral with respect to arc length over that curve would be given by this formula. It's a natural extension, right? It's a natural extension. And hold on here. We have an additional formula where we have a line integral with respect to z. And so you would have z prime of t dt at the end. And then if you wanted to find the sum, of three line integrals, that would be how you notate it. And example 6 has a nice example in the book where they are finding the sum of three line integrals and your path hold on now, your path consists of two line segments. And the line segments are given in this picture here. And they show you the work involved in that. And I'll let you read that on your own because I'd like to, I'd like us to keep going here. Well, I'll tell you what I'm going to do. What I want to do, I want to give you a little break here, an 8-minute break till 7:55. So let me stop this recording. Are there any questions? All right, I'm going to stop this recording. We'll continue on with section 13.2 in our next little lesson. It'll be in the next recording. We're going to talk about line integrals of vector fields. Okay.